Video I'd like to talk about bases as described in chapter 14.6. Let's review our definitions of bases according to the theories we learned about earlier in the unit. According to the Arrhenius definition or model of acids and bases, a base is a substance that increases the concentration of the hydroxide anion when you place it in water, whereas a Bronsted-Lowry base is a proton acceptor. What are strong bases? Well, a strong base is a metal hydroxide salt that, when it dissolves in solution, completely dissociates. And here is an example of an equation that represents a metal hydroxide salt dissociating to form the metal cation and hydroxide anions. The most common strong bases are sodium hydroxide and potassium hydroxide because they are cheap. The other group 1 metal hydroxides are also considered strong bases, but they are less common. The Group 2 metal hydroxides, for example, calcium hydroxide, strontium hydroxide, and barium hydroxide, are only slightly soluble, but to the extent that they dissolve, they do dissociate completely, so I suppose we could consider them to be strong bases as well. How do we calculate the pH of a strong base solution? Pretty much by composition. We use stoichiometry to figure out what the concentration of the hydroxide anion is, and from that we use our definitions of pH to calculate pH. So in this problem, we are given a certain amount of potassium hydroxide, dissolved in enough water to make a certain volume of solution. So let's calculate the hydroxide ion concentration, from which we will calculate the pH. Let's begin by writing out an equation to represent the dissolution and dissociation of potassium hydroxide. Solid potassium hydroxide dissolves and dissociates in water to form the potassium cation plus the hydroxide anion. Here's our roadmap. Mass of potassium hydroxide will allow us to calculate the moles of potassium hydroxide, which will allow us to calculate moles of hydroxide, which in this case is a 1-to-1 mole ratio, but it doesn't have to be, which will let us calculate the concentration of hydroxide, from which we'll determine the pH. So let's begin by calculating the hydroxide ion concentration. So I have 0.219 grams of potassium hydroxide divided by the molar mass, 56.11 grams per mole, times 1 mole of hydroxide for every 1 mole of potassium hydroxide. And we'll divide that by the total volume of solution to give us 0.00156 molar hydroxide ion. Now, my pH is the negative logarithm of the hydrogen ion concentration. If you want to, you could calculate the hydrogen ion concentration and plug into that, but here's a little shortcut. We know that pH is equal to 14.00 minus POH, but POH is simply equal to the negative base 10 logarithm of the hydroxide ion concentration. So a short form of calculating pH when you're given the hydroxide ion concentration is pH equals 14.00 plus the base 10 logarithm of the hydroxide ion concentration. So I'll take the base 10 logarithm of 0.00156, and that gives me a pH of 11.19, which is well above pH 7, which is consistent with a basic solution. Now, we could go in the other direction. Suppose I give you a solution of strontium hydroxide for which I know the pH, and I want to know what the molarity of strontium hydroxide is that will give us that pH. Once again, let's begin by writing out an equation to represent the dissolution and dissociation of this particular hydroxide salt. Strontium hydroxide dissolves and dissociates to form strontium cations plus, 2 moles of hydroxide for every 1 mole of strontium hydroxide. Since I have the pH, I know that lets me calculate the hydroxide ion concentration, because the hydroxide ion concentration is 10 to the minus POH, but POH is 14.00 minus pH, so I can write this as 10 to the negative 14.00 minus pH, or 10 to the negative 14.00 minus 10.50, or my hydroxide ion concentration equals 3.2 times 10 to the negative 4th moles per liter. Now, the question is, what's the concentration of calcium hydroxide? strontium hydroxide. So it looks like I'll need a mole ratio here. My concentration of strontium hydroxide equals 3.2 times 10 to the negative fourth moles of hydroxide per liter of solution times 1 mole of strontium hydroxide for every 2 moles of hydroxide, or my concentration of strontium hydroxide equals 1.6 times 10 to the negative fourth mole. And if the question asked what mass of strontium hydroxide would I need to make a specified volume of that concentration, you could simply use the molar mass. Now, what is a weak base? This is important. A weak base is a molecule, which is neutral, or an anion, which has a negative charge, that partially ionizes in water by accepting a hydrogen ion from water. And I can write equations to represent this. Here I show a neutral basic molecule, B, reacting with water in an equilibrium to form BH plus the conjugate acid plus hydroxide. Notice that the structural feature that the base must have in order to accept a proton from water is a lone pair. That's why I wrote B with a lone pair on it. Okay? Or, if my base is negatively charged, that is, if it's an anion, it can accept a proton from water to form the conjugate acid HX plus hydroxide. Please pay attention to charge balance. When the base accepts a proton from water, the conjugate acid has a positive charge that is 1 greater because it accepted the hydrogen as a hydrogen ion H+. Notice also that the conjugate base, which is hydroxide in both of these cases, the charge is 1 less than the acid water because it lost H+. Okay? Now, notice that in both cases, these bases behaved both as an Arrhenius base because they increased the hydroxide concentration of water, as well as a Bronsted-Lowry base because they accepted a proton from water. And we can write a Kb expression, as we would expect. It's equal to the concentration of the conjugate acid times the concentration of hydroxide divided by the equilibrium concentration of the base. Common weak bases are amines. Amines are a class of organic molecules in which a nitrogen atom forms bonds to 3 other things, which could be hydrogen atoms, they could be carbon-based groups, they could be other things, but the crucial structural feature that the amine base must have is a lone pair. Again, it needs a lone pair in order to accept the proton from water. Okay? An example of a common amine would be, of course, ammonia, a very common base. So, where do we find weak base ionization constants? In a table of weak base ionization constants. Where else? You will always have access to this if you need it. So, let's write a balanced equation to represent the ionization of dimethylamine in water and write the corresponding Kb expression. Dimethylamine is an amine that has 3 things attached to it, 2 CH3 groups, which are methyl groups, plus a hydrogen. It reacts with water in an equilibrium to form the dimethyl ammonium cation. Notice that I show the base accepting a proton, so it has an extra H on it plus a positive charge, and remaining behind after the water gives away H plus is the hydroxide anion. Kb expression will be equal to the concentration of the dimethyl ammonium ion, the conjugate acid, times the concentration of hydroxide, divided by the equilibrium concentration of unionized dimethylamine. So, how do we calculate the pH and all solution concentrations of a weak base solution? Pretty much the same way we did with weak acids. We write out the ionization expression and the Kb expression, like we just did in the previous slide, and then, as we learned in chapter 13, we use an ice table to solve for X. In this case, X is not the concentration of hydrogen ion, it is the concentration of hydroxide ion. So let's do an example. Calculate the hydroxide ion concentration, the hydrogen ion concentration, the pH, and the percent ionization of a 0.20 molar solution of ammonia. So let's begin by writing out the ionization equation. Ammonia reacts with water to form the ammonium cation plus the hydroxide anion. Kb is equal to the product of the concentration of the ammonium ion and the hydroxide ion divided by the concentration of unionized ammonia, which is equal to 1.8 times 10 to the negative fifth. I got that from the table of Kb values. As we did before, I'll set up my ice table. Here's ammonia. Here's the ammonium cation. Here's the hydroxide anion, ICE. My initial concentration of ammonia is 0.20. My initial concentration of ammonium is 0. My initial concentration of hydroxide is not 0, remember? It's equal to 1.0 times 10 to the negative 7th molar from the background ionization of water, but that's effectively equal to 0. I'll define my change as the decrease in concentration of ammonia, the increase in concentration of ammonium, the increase in concentration of hydroxide. So this becomes 0.20 minus x, x. So plugging these into my Kb expression, I get x squared over 0.20 minus x equals 1.8 times 10 to the negative fifth. Kb is pretty small, so I'm going to make the simplifying approximation that x is negligible in comparison with the initial concentration of ammonia. And from that, I solve x equals the square root of the initial concentration of ammonia times Kb, which is equal to 1.9 times 10 to the negative third molar, is equal to my concentration of hydroxide and of the ammonium cation, the conjugate acid. The hydrogen ion concentration is Kw over the hydroxide ion concentration equals 1.0 times 10 to the negative 14th over 1.9 times 10 to the negative third. Pause for 1 second while I grab my calculator. Forgot to do this one in advance, sorry about that. Go get a cup of coffee or something while I'm calculating. And that gives me 5.3 times 10 to the negative 12th molar as my hydrogen ion concentration. The pH equals the negative base 10 logarithm of the hydrogen ion concentration, 5.3 times 10 to the negative 12th, which is equal to 11.28. Again, consistent with the basic solution, well above 7. And finally, for the percent ionization, that's equal to the concentration of hydroxide divided by the initial concentration of ammonia, or 1.9 times 10 to the negative third molar, over 0.20 molar times 100, which is 0.45% ionization. Remember, when we calculate the percent ionization, we are implicitly checking the 5% rule. Remember, the simplifying approximation of neglecting x in the denominator of the Kb expression is justified if, after doing so, you find that x is less than 5% of the quantity that you subtracted it from. In this case, that is equal to the percent ionization. 0.45% is significantly less than 5%, so we are justified. Can we calculate Kb if we are given the initial concentration of base and the pH of equilibrium? This is very similar to problems that we've done before in Chapter 13 and earlier in Chapter 14. So here we have codeine, a derivative of morphine that is used as an analgesic. If I give you the pH of a solution and we know the initial concentration, can we calculate Kb? Well, I'm going to begin by writing out an equation for the ionization, but I'm going to simplify. I don't want to be writing C18H21NO3 every time. So I'm just going to represent that neutral basic amine as B. So here's the ionization of B in water to form the conjugate acid plus hydroxide. I'm going to want to be plugging equilibrium concentrations of these species into the Kb expression in order to calculate Kb, so let's leave that there for the time being. This is the type of problem where you are given an initial concentration, you are given some information about what's present at equilibrium, and you are using that to calculate all of the equilibrium concentrations, and from that, Kb. What information are we given about the equilibrium position? We are given the pH. which lets us calculate the hydroxide ion concentration. So the hydroxide ion concentration at equilibrium, which is equal to the concentration of the conjugate acid at equilibrium, is equal to 10 to the negative POH, which is equal to 10 to the negative 14.00 minus pH, because we're given pH, equals 10 to the negative 14.00 minus 9.59. So the concentration of hydroxide is equal to the concentration of the conjugate acid at equilibrium, which is equal to, when I evaluate the final expression, 3.9 times 10 to the negative fifth moles per liter. Now, so there's two of the terms that I want to plug into the Kb expression. The third one will be the equilibrium concentration of unionized base, which is going to be my initial concentration, 1.7 times 10 to the negative third molar, minus the amount by which that concentration decreases, which is equal to the increase in concentration of hydroxide in the conjugate acid. So I'll subtract 3.9 times 10 to the negative fifth molar, and as you might expect, that is negligible in comparison with the initial concentration, so that remains at 1.7 times 10 to the negative third molar codeine. So now I can simply go back up and plug these equilibrium concentrations into my Kb expression to solve for Kb. 3.9 times 10 to the negative fifth quantity squared over 1.7 times 10 to the negative third, or a Kb value of 9.0 times 10 to the negative 7. Again, we use the initial concentration of the weak base and the measured pH at equilibrium to solve for the equilibrium concentrations of all components, and from that, Kb. One final problem that's a little bit challenging: what mass of pyridine, a weak base for which Kb is given, is needed to make a specified volume of a solution that has a specified pH? Well, let's begin by writing out our equation for the ionization. Never hurts to start with what we're given. Pyridine reacts with water to form the pyridinium ion. I write the conjugate acid as C5H5NH plus to indicate that the hydrogen ion that's being removed from water associates with the nitrogen. If you wrote it as C5H6N plus, that would be fine, but this is a bit clearer as to what exactly is going on. So, in order to solve for the mass of pyridine, I think what we're going to have to do looks something like this. The pH is going to let us calculate the hydroxide ion concentration. And from the hydroxide ion concentration, using Kb in the Kb expression, we're going to need to calculate the concentration of pyridine, the initial concentration of pyridine, which I think is going to let us calculate the mass of pyridine needed using the volume and molarity. Okay, so let's begin. So my hydroxide ion concentration equals the pyridinium ion concentration equals 10 to the 14.00 minus pH, 10 to the negative 14.00 minus 9.50 equals 3.2 times 10 to the negative fifth molar. If I look at my Kb expression, Kb is equal to the concentration of the conjugate acid times the concentration of hydroxide. Notice I just calculated both of those at equilibrium, divided by the concentration of base at equilibrium. I have three of those, and I'm trying to solve for the fourth. So let's rearrange to isolate the concentration of pyridine, C5H5N. So that's equal to the product of the concentration of conjugate acid and hydroxide divided by Kb. Now notice what we're assuming here is that the equilibrium concentration of pyridine is equal to the initial concentration. And I think that's going to be valid because the amount by which that concentration decreases, namely 3.2 times 10 to the negative fifth, is pretty small. So let's just plug in and see what we get here. 3.2 times 10 to the negative fifth quantity squared over 1.7 times 10 to the negative ninth equals 0.60 molar as my equilibrium concentration of pyridine. And we can see that if we were to add to that 3.2 times 10 to the negative fifth, that would be totally negligible. Okay, so we have our concentration of pyridine required to give the specified pH. Now we simply need to calculate the mass of that substance needed to prepare the specified volume. Well, if we're going from molarity to moles to mass, we know we're going to need molar mass. So let's calculate the molar mass of pyridine. So let's see, 5 times the molar mass of carbon plus the molar mass of hydrogen. Oops, left off a digit there. Plus the molar mass of nitrogen is 79.10 grams per mole. So, my final step, the mass of pyridine needed to prepare a specified volume in pH is going to be equal to the molarity, 0.60 molar, times the specified volume, 0.500 liters, times the molar mass, 79.10 grams per mole. So the mass of pyridine needed is equal to the two significant figures, 24 grams. So if I dissolve 24 grams of pyridine in enough water to make half a liter of solution, I will have a pH of 9.50. Great. In the next video, we will talk about polyprotic acids. See you then.